If you are a science student, I'm sure you are somewhat familiar with this number. If you may recall, it might have appeared in your high school chemistry class, or perhaps in an introductory physics class you have heard about the atomic model. Perhaps it is out of curiosity that you asked your teacher what is the energy of an electron, and what you get is this rather mysterious number. Or perhaps you have seen the energy level equation in your waves mechanics class, which explains the transition energy of an electron in a hydrogen atom. Now this equation looks clean, but if you are a little bit more involved in the physics community, you might know that getting this equation is not the easiest task. To be precise, to obtain this equation, we need to solve the Schrödinger's equation for the hydrogen atom. If you are confused, this is okay. Physics college students take years of class after high school to prepare for quantum mechanics. And I find this problem hard even after taking all these courses. It was long, several pages of derivation with some rather tedious calculations. However, I do not think it is impossible to simplify it to a level that can be easily understood by people with little scientific background, at the very least in a more than hand-wavy but far from rigorous way. You just need to know some very simple physics, some basic calculus and probability, perhaps linear algebra, and do a few algebraic manipulation tricks. This will be the first episode of a multi-part video series that will begin with some big pictures of quantum mechanics, and then eventually go into finer details and solving some well-known quantum mechanics problem. By the end of this video, I am hoping that you will be familiar with some conceptual quantum quirkiness and get ready to tackle Schrödinger's equation in the following video. Before we begin actual quantum mechanics, I want you to think about something rudimental, something too simple about classical physics that might often be overlooked. I am asking, how might a physicist describe some everyday objects? Well, there are essentially like 3 important steps. We will first assign properties to the object. For example, an apple might be classified by where it is located at, which is its position, and where it is moving to, its momentum. Secondly, we need to get some coordinate system. Like for example, if we are interested in position, we might use 2 basis vectors to assign a 2D Cartesian coordinate system. Maybe another momentum coordinate system telling us where it is going. Setting up the coordinate system allows us to represent the property we are interested in through some mathematical way. Like the position representation of the apple is a vector, which is a set of numbers. And lastly, we make measurements. For example, when we say the position of the apple is located at 4,2, what we really meant is that the apple is located 4 units along the x-axis and 2 units along the y-axis, with respect to the origin, of course. Here we simply just need to read off the value displayed on the coordinate system. I have to point out the subtlety between the position representation and the position we get after measuring a value. You might think it is overcomplicating it, and yes, that is true. In classical physics, they are similar. We generally do not consider them as 2 different steps. But you will see later that quantum mechanics actually highlights a difference here. Now let's begin exploring. I want you to imagine 2 objects. A regular apple like the one I was just describing, and a quantum apple, which I will use to describe in a quantum manner using the same 3 steps. And just for the sake of simplicity, I'm going to reduce the position and momentum dimension to 1. In the quantum world, quantum objects, like our quantum apple, are governed by what is called a quantum state. We generally use angled bracket called a cat with a psi in it to denote it. A state is sort of equivalent to the object itself. We have properties like position, momentum, energies, and etc., and those are all contained internally within the state. And eventually you will see that there are ways to extract those properties out. That's it, simple as that. But I want to mention something different here. When we are assigning a property in quantum mechanics, we are not guaranteed that they can take up any value we like. We can generally classify properties into two types. First, there are properties in nature that only discrete values are allowed. For example, spin, which will not be the focus here, and also orbital angular momentum. I want to emphasize when I talk about properties being discrete, I really meant it. Nature is very biased, and there are certain values in nature that are simply not allowed. For example, we can never have an angular momentum value of 3.32 h bar at any circumstances. And that is because angular momentum has to take on integer multiples of h bar. I also want to highlight the number allowed in angular momentum is bounded by m, which we call the magnetic quantum number. This can be counterintuitive when we try to apply quantum mechanics on some macroscopic objects. But keep in mind that our standard unit of angular momentum, h bar, is a very, very small number. Which means that to get angular momentum value that is sensible in real life, the upper limit of angular momentum, which is m, needs to be very large. So we approximately see them continuous in real life. Secondly, there are properties that can take up any value. For example, position and momentum. They are, of course, a lot less interesting because they are essentially the same as the one in classical mechanics. Here, I want to mention a really important terminology, and I want you to memorize it. We call the allowed value of some property the eigenvalue of that property. And that is for some mathematical reason due to its connection to linear algebra. Now that we have a state psi representing our quantum apple, the second step is to set up a coordinate system. In quantum mechanics, we can mathematically represent a quantum state living in some coordinate system by sticking this leftward-facing bracket known as a bra to it. If we are instead interested in setting up a momentum coordinate system, we can write the momentum symbol P instead, but I will stick with X for the analysis, and you can imagine doing the same thing with momentum because the logics are the same. In this notation, on the left-hand side, you should really read it as given some particle psi, in our case, the quantum apple, what is the representation of that state in the position coordinate system X? Now look at the right-hand side. We have psi of X. What does that mean? This is where things get interesting. Think about a single dimension in a classical system. When we are talking about the location of an apple on the x-axis, ultimately our goal is to describe the position x with some number. So we can write the position representation of the apple equals to the number x, its measured position. The left-hand side of both highlighted equation here physically represent the same clause. It is just that quantum way has a fancy notation. Now on the right-hand side, it seems like quantum mechanics is suggesting the representation of our quantum apple in x position coordinate system is so-called a wave function. This is definitely uncharted territory, because seriously, it does not really make any sense to say our quantum apple is located at some very complicated function location. And I'm hoping I have motivated you enough to believe that the position coordinate system does not necessarily tell us about the precise position. The takeaway is, in quantum mechanics, we make the distinction between the measured physical quantity and the coordinate representation of that quantity. And in general, they are not equal. The thing is, when we think about classical mechanics, representing an object in a coordinate and making a measurement based on it is essentially the same. If we already know the apple is at some position, the only thing that can change it is through some equation of motion that depends on time. In quantum mechanics, this is not the full story. Yes, we do have an equation of motion called the Schrodinger's equation that changes the state and hence the position over time. But there is also some sort of inherent randomness when measuring. The reason we have this phenomenon is because certain quantum properties, they can be intertwined, like position and momentum. For example, if we are given position coordinate system and a momentum coordinate system, measuring position will actually change the momentum and vice versa. You might have heard about the Heisenberg uncertainty principle, and there are actually a set of them. But the most famous one is on the screen right now. The triangle here is the statistical variance of repeated measurements, taking account of the randomness. It is associated with a range where we are around 68% sure about where the measurement is going to land. The takeaway of this equation is that for two incompatible properties of a quantum object, maximum certainty in a single quantity means maximum uncertainty in the other. So here, if I know the exact position of our quantum apple, then I'll have no idea what this momentum is. To re-emphasize what we have learned here, quantum object measurements are not always the same across different trials, and the source of randomness comes from the incompatibility of properties captured by this principle. And that is why we should not really assign exact quantities to properties. Now the last step is to talk about how precisely we can make a measurement. Since wave functions are coordinate representation of our quantum apple, it should at least capture the probabilistic/uncertain nature of measurements that we were talking about. How this works is proposed by Max Born. The wave function in some coordinate system, when squared, is the probability density function of measuring the associated property of the coordinate system. And from probability theory, when you integrate a probability density function, you expect the area under the curve gives us the probability itself. And of course, there are nothing preventing us to doing the same with momentum. But I will stick with position here. I do want to make a few remarks here. First, a probability density function requires the sum of all probability across all positions is 1. When dealing with different equations in quantum mechanics, this characteristic is not always automatically satisfied. To enforce this characteristic is called normalizing the wave function. And second, most of the time our wave function is generally a complex function. That means that this function might contain this weird number I equals square root of -1, and it can certainly be pretty weird to interpret it at first, because I is not physical. But think again, the wave function does not necessarily has to be physical. Yes, it does represent a physical object, but after all, it is just a mathematical tool to describe our quantum effect. And as long as the measurement made from the wave function are physical, then our tool wouldn't cause any trouble. Now we know how the wave function relates to the probability of measurements. How about making measurement itself? Well, we do so by placing what we call an operator next to the state or a wave function. These are properties with a little hat on it. Note that when measuring, we can measure directly on a quantum state, so the coordinate is not absolutely necessary. But it is certainly very useful to have, because that's how we can actually draw values from the probability distribution. Also note that we are allowed to extract position of an object represented in the momentum coordinate system, and that is totally fine. Wave function is just a representation of the state itself, which means that it must have contained information about all properties we are interested in. We just need to convert the operator to the appropriate coordinate system. We can of course do all kinds of probability measurements using them, but these will not be our focus of today. I want to mention a very subtle but useful way to think about the probabilistic nature of value here. Since eigenvalues represent all possible outcomes of a measurement, we can imagine a pool of quantum states of some property like position. And for each of the states, we demand that when measured, it will guarantee with 100% certainty yield the same eigenvalue every time. In this way, we can make a one-to-one association between eigenvalues and those states, which we call them eigenstates. We can represent an eigenstate by using a cat and put this eigenvalue inside it. As a side note, I want to briefly mention that we can indeed have eigenstates corresponding to multiple physical properties. This of course cannot happen if the properties are incompatible with each other, because in that case it would just break the uncertainty principle. We can't know the position and the momentum simultaneously. This is a very complicated topic on its own, so I will not discuss the details here. You might have noticed mathematically when applying an operator on a specific position eigenstate, we do not merely get the position, but rather the position multiplied by the state itself. These equations are called eigenvalue equation, and it is mathematically structured in this way to represent a ground truth about measuring these special, carefully constructed eigenstates. And these equations are particularly useful because depending on the property, the eigenvalue equation can be either matrix or differential equations. So if we have some unknown properties, then we simply have to just set up one of these equations and solve for it to get all the eigenvalues, eigenstates, or eigenfunction. In other words, when we are given a system, then it is always possible to obtain the eigenvalues and its corresponding state given some quantity. Maybe not always analytically possible, but at the very least numerically possible. Well, measurements on eigenstates is kind of straightforward because they are non-probabilistic. For a general object, it might take on any allowed value with some probabilistic weight associated to it. When we make a measurement, we should really think about sampling from the pool of eigenstates. Physicists are kind of troubled to interpret this result, because probability means that we really cannot assign a single eigenstate to an object. And that would mean that our quantum apple cannot be in one position. Well, disappointingly, physicists cannot really agree on a united physical interpretation for this. The most popular interpretation, which is the one generally taught in the textbook, is called the Copenhagen interpretation. In popular media, this interpretation is most often associated with Schrödinger's cat. It says that an object, like our quantum apple, is in a superposition of all eigenstates, so it exists in all states, until a measurement will collapse the object into a single eigenstate. Notice that after the measurement, the object now becomes the eigenstate, and now repeated measurements will always give the same respected eigenvalue. The part where our original probabilistic state turning into a definite value state after a measurement should make some philosophical sense, because otherwise there will be no meaning of a measurement. Oh, and one last thing. Since we have measured and known the exact position now, don't forget about the Heisenberg uncertainty principle. Knowing the exact position will mean that we have no idea about its momentum because of maximum uncertainty in momentum. Hi, I'm Yi Chen. Thank you for watching until this part of the video. It's been quite a journey. We have talked about how a physicist might use 3 steps to describe an everyday object. First, we'll assign properties to the object. Second, we'll attach a coordinate system to it. And third, we'll use the coordinate system to make some measurements. We've seen that classical mechanics and quantum mechanics are quite different in all 3 of those regards. Well, as a review, quantum properties can only take on certain allowed values called eigenvalues. We also talked about properties that can be interacting with each other through the Heisenberg uncertainty principle. And we have also seen the wave function as a probability distribution, capturing the uncertainty in measurements. Lastly, we discussed about the eigenstates and the Copenhagen interpretation of quantum mechanics. The next video will be more of a math/application one. We'll be introducing the Schrödinger's equation and perhaps go through the algebraic process of solving the hydrogen atom that leads to the energy separation equation we have seen in the beginning of this video. Making those videos generally take a lot of time and energy, so if you enjoyed this video so far, please consider like and subscribe to the channel. That will be a big help for me. I'll see you on the next one. Peace out.